This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. This video will be an introduction to solubility, so the first thing we'll go over is the concept of dissolving compounds, and then we will do an introduction to the solubility constant. Any question on the MCAT that is dealing with solubility or concentrations is going to have water as a solvent. And water can disrupt ionic bonds and some intermolecular forces. And so first we're going to look at ionic bonds and then talk about intermolecular forces and discuss how water does this. On the image on the left, we have sodium chloride being dissolved by water. First, we need to think about sodium chloride outside of water. The positively charged sodium is attracted to the negatively charged chloride ion, and they have an ionic bond that's holding them together. When we put this molecule into water, remember that water is polar, and the positively or the partially positive hydrogens line up with the negative chloride ions, and the partially negative oxygens line up with the positively charged sodium ions. And then those charges start to interact. So the oxygens interact with sodium and the hydrogens interact with the chloride ion. Eventually, the ionic bond between the chloride ion and the sodium starts to break and will completely break as those atoms get totally surrounded by water molecules. This process is called dissolving, and then after this happens, sodium and chloride would be considered aqueous. And the degree to which something dissolves varies very widely depending on what compound it is. So something like sodium chloride almost completely dissolves. Basically, like 100% of the molecules that go into water will dissolve into those two ions. But for some ionic compounds, it's actually going to be a super small percentage that actually turns into the ions. And you don't need to really worry about the why, but later in this video and the next video, we're going to elaborate on how you calculate exactly how much of a compound is able to dissolve. On the right side, we're going to look at how a non-ionic compound would dissolve. And sugar is a really good example of this, and it's something that most people have seen in real life by putting sugar in water. So here we have two sugar molecules, and sugar has a lot of OHs. And remember that OH is really polar. So because it has a lot of those OHs, two sugar molecules can stick together really well because of the strong intermolecular forces. So these are not ionic bonds that hold sugars together because it's only partial positive and partial negative charges, but there are really strong intermolecular interactions. And then the same thing happens when we put that into water. The polar water molecules then start to interact with the polar parts of sugar, and it breaks away those two molecules of sugar. The big thing that you just want to be really aware of is that those sugar molecules don't have charges. And one other thing to note is that entropy, so the delta S, always goes up when something dissolves. And this has to do with the idea that the more water can interact with the molecules, the higher the entropy. And that's going to come up again with protein folding and any time that there's something that's getting dissolved. When something is dissolved in water, you're going to need to be able to calculate the concentration of it. And the unit of concentration that's used in all solubility questions will be molarity. And molarity is this equation here where it equals the moles of whatever compound you have divided by the liters of your solvent, which is almost always going to be water. You need to be really fluent in your ability to go from molarity to moles or from moles to molarity. And we'll just do a quick couple examples here just to illustrate how quickly you can do this. So if we have a solution of sodium sulfate and we are given the concentration of 5 molars, and then we're asked to find how many moles are in 5 liters and then how many moles are in 0.5 liters. So for this one, you want to set it up as X moles divided by 5 liters, because we're told that's how many liters, equals 5 molar, because that's the concentration that was given to us. And then you just solve for X, so X would equal 25. You set it up the exact same way on the right, so we do X moles divided by 0.5 liters equals 5. And then when you multiply 5 by 0.5, you get 2.5 moles. And you need to be able to solve for any variable in that equation. Now we're going to look at dilutions. And dilutions is just whenever you are changing the volume of a solution, but you're not changing the amount of your solutes that are in that solution. So here we have a 30 milliliter sample of a solution, and let's just say this is the same solution that we've been using before, which is sodium sulfate. and its concentration is 5 molar. So first, let's think about how many moles are in this first solution. And we're going to solve this the exact same way as before. So that's X over 30 milliliters. And here's a good practice in how to solve these math problems a little bit quicker. So instead of writing 30 milliliters, let's just instantly convert this to liters. So it's 30 times 10 to the negative 3 liters. And that equals 5 molar. So now we just need to do 5 times 30 times 10 to the negative 3, which that would equal 150 times 10 to the negative 3 moles. And then we add 20 milliliters to it. So we've added 20 milliliters to get to 50 milliliters. The way you want to think about this is the number of moles has not changed. So now what we're simply dealing with is 150 times 10 to the negative 3 moles divided by 50 milliliters. So 50 times 10 to the negative 3 liters. And we use this to figure out what the new concentration is. Because dilutions change concentration, they do not change the amount of the moles in your solution. I'll do a whole nother video on the math here, but just real quick, you want to separate this math as 150 divided by 50 and do that first. So that would be 3. And then you separately do 10 to the negative 3 divided by 10 to the negative 3, and that's just going to equal 1. So your final answer here would be 3 molar. Now this next part is another situation you might see where we start off with our 5 molar solution, our 30 milliliters, so that first vat, and then we take a small sample from it. So we took 5 milliliters from our first vat and put it in this test tube. The concentration stays the same because that's a uniform concentration. So if we take any portion of our original sample in this vat, it's going to have the exact same concentration as any other portion of that sample. So our 5 milliliter solution has a concentration of 5 molar, but we don't know how many moles are in that solution. So we set it up as X divided by 5 times 10 to the negative 3 equals 5 molar. And 5 times 10 to the negative 3 would give us a value of 25 times 10 to the negative 3 for the number of moles in that solution. And now we're just back to doing a normal dilution problem. So we add 5 milliliters to this solution to get our 10 milliliter solution. So we've just added water. So that means that the number of moles has stayed the same. So we do 25 times 10 to the negative 3 moles divided by our total of 10 milliliters, which is 10 times 10 to the negative 3 liters. Do your 25 divided by 10 first, and that would give you 2.5. And then your 10 to the negative 3 divided by 10 to the negative 3 equals 1. So you just end up with a value of 2.5 molarity. In the last part of the video, we're going to start getting into how you figure out how much of a compound will dissolve. The first thing that we need to go over is how to recognize something that will completely dissolve. A super simple way to start to get to a mastery of this is to memorize this list. So if a compound contains group 1 metals, so anything that's in that first column of the periodic table, anything that has that in it is going to completely dissolve into the group 1 ion and then whatever anion is attached to it. The next would be if anything is attached to the ammonium ion. And remember from one of the videos way back, we talked about ionic compounds. So if you need to refresh on the idea of polyatomic ions, then I would go back to that. But ammonium is a polyatomic ion that will combine with an anion. So regardless of what anion that's attached to, that compound will be completely soluble. And then the same would be said for the nitrate ion. No matter what cation nitrate is attached to, the compound will be completely soluble. And this is a really short list compared to a lot of the ones that you're going to find online. I would highly recommend you just start with this one and then only worry about memorizing the rest of them once you have pretty much mastered all the high yield stuff, because the other things on that list are going to be way less common than these 3 things, and I'm not sure it's really ever worth your time to memorize those ones. Here are some compounds that I just want to point out because they are super common, just so you're a little bit more prepared specifically for these. So sodium acetate comes up a lot, especially in acid-base problems. Acetate is it's more of an organic compound, so there's the structure of acetate, but here is the molecular formula for acetate. So just kind of familiarize yourself with what acetate looks like as a structure and by its molecular formula. And anytime that it's with sodium, according to the rules above, it is going to completely dissolve. Next is sodium sulfate, and same thing, this is heavily involved with acid-base problems, and sodium sulfate will completely dissolve into 2 sodium ions and 1 sulfate ion. And then next is sodium in any base, which is pretty much what the 2 examples were above, but anytime sodium is with the conjugate base of an acid, which conjugate bases we will cover way more in a future video over acids and bases, but anytime sodium is with that base, it's going to completely dissociate. And what you're doing is you're basically just adding a bunch of that base, and then sodium remains a spectator ion throughout the rest of the problem. On the right side, we have a list of polyatomic ions. And just like the completely soluble compound list, this list is quite a bit shorter than other ones that you'll see online. And I would not worry about memorizing more than this list, because the rest of the polyatomic ions that will be on those lists are significantly lower yield, and you are most likely way better off spending your time learning higher yield material before you even think about memorizing more polyatomic ions. And this is a really good example to use when talking about not wasting your time memorizing things that you're going to be able to commit to memory just through practice problems. So I'm going to go through a lot of these ions and point out why you probably shouldn't worry about memorizing them, because you're going to see them so much in other types of problems that you're just going to commit them to memory by default through doing practice problems. So acetate and ammonia will come up so much with acid-base problems that you're going to have those committed to memory. Bicarbonate and carbonate will come up in the bicarb buffer system, so those should be memorized. Hydronium ions and hydroxide ions are the 2 most important ions with acid bases, so those 2 will probably be memorized. Nitrate and nitrite, those 2 are actually ones that I probably would memorize, because they're not really going to come up naturally in a lot of practice questions. Phosphate will come up all the time with phosphorylation, so I wouldn't really put in extra time for that. And sulfate will come up a lot with acid-base problems. Finally, in the last part, we're just going to start introducing how you calculate the concentration of the individual ions after you dissolve a compound in solution. So for this first one, we're saying that we're dissolving 5 moles of sodium sulfate into 1 liter. So it's a really simple problem, but we just need to do it to make sure we're clear on one important thing. First, identify this as a completely soluble compound because it has sodium. So that means that every single molecule of sodium sulfate will dissolve into 2 separate sodium ions and 1 sulfate ion. So if we have 5 moles of sodium sulfate, then what that means is we're going to have 10 moles of sodium ions. And then we're only going to have 5 moles of sulfate because we only have 1 molecule of sulfate for every 1 molecule of sodium sulfate. So when you find the concentration of each of those, you would have a concentration for sodium of 10 divided by 1, so that would be a concentration of 10 molar. And then for sulfate, your equation would be 5 divided by 1, so that would be a concentration of 5 molar. Next, let's look at silver oxide. And notice how nothing in this molecule appears in the list of completely soluble compounds. So this is when the idea of KSP gets introduced. And in the next video, we're going to completely dive into KSP and exactly how we use that. But just know that when something is not completely soluble, it's not as simple as what we did above, and you're going to have to start using KSP problem approaches.